Question number 1 is a binomial distribution. It says suppose that 80% of adults with allergies report symptomatic relief with a specific medication. If the medication is given to 10 new patients with allergies, what is the probability that it is effective in exactly 7? We put our numbers into GeoGebra. It's a binomial distribution. Our n is 10, so it's 10 new patients. Our probability is 0.8, it's our 80%. We want to know what's our probability of getting 7, so we put that in down here at the bottom. Probability of 7 is going to be 0.2013. And I love how GeoGebra puts all the different values for the different possibilities so that you could figure any of those if you wanted to as well. Question 2. This just says, births at a hospital randomly occur at an average rate of 1.8 births per hour. What is the probability of observing 4 births in a given hour? This one is a Poisson distribution. We have an average rate there of 1.8. We want the probability of getting 4 births. Again, it gives us all of our numbers. It shows us our graph. It gives all the different possibilities. And you can see there where 4 is 0.0723. We have our mean and our standard deviation there. Part 2b says, what is the probability of observing 5 births in 2 hours? So this time I changed the rate to be 3.6 here. The probability of getting 5. There's our graph, our histogram. And over there it gives us all of our values possible. From 0 all the way up to 13 is the last one where we'd have a value. At 14 you have 0 probability. Question 3. Intelligence quotients measured as the standard revision of the Binet-Simon intelligence scale are normally distributed with a mean of 100 and a standard deviation of 16. Determine the percentage of people who have IQs between 115 and 140. This one is a normal distribution. Switched it to normal down here for GeoGebra. Our mean is 100, our standard deviation is 16, and it figures it for us. We want to get the probability between 100 and 140 people, people with 115 and 140 IQ is 0.168. That's the area under the normal bell curve here. That's the area underneath that curve, which is 0.168 of the total curve. Question 4. One of the larger species of tarantulas is the Grammostola malacoma, whose common name is a brilliant giant tawny red. Tarantula has 2 body parts. The anterior part of the body is covered above by a shell or carapace. From a recent article by F. Costa and F. Perez Millis titled Reproductive Biology of Uruguayan Theraphoids, we find that the carapace length of an adult male is normally distributed with mean of 8.14 millimeters and standard deviation of 1.76. We're going to find the percentage of adult males that have a carapace length between 16 and 17. So this one is again another normal distribution, a bell curve, a mean of 18, pretty close to 18, 18.14, standard deviation of 1.76. We enter our numbers down there in GeoGebra. And then we want to find out the probability of between 16 and 17 millimeters for the lengths. And it figures it for us as 0.1466, which is the area under this normal bell curve. Part B says find the percentage of adult males that have a carapace length exceeding 19 millimeters. GeoGebra has this really neat little thing that you can do the smaller than values, larger than values, or in between values. So I switched it to the larger than, so we wanted greater than 19 millimeters, and put in 19 there, and it came out at the area under the curve from 19 going to the right is 0.3125. So about 31% of the spider population will have a carapace of greater than 19 millimeters. Question 5 was a uniform distribution, a little bit different. The amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 15 minutes inclusive. What is the probability that a person waits fewer than 12.5 minutes? Since it's a uniform probability distribution, percentage is fewer than 12.5 minutes. The lower bound is 0, the upper bound is 15 here. And that gives us a probability for the lower part. Below 12.5 would be 0.833, and above 12.5 of 0.1666 repeating. Okay. And our curve looks like this because it's a uniform distribution. Thank you very much.